breaking symmetry. For decades now, the exact composition of matter in the universe has baffled astronomers and physicists alike. It would seem that, given the basic assumptions about the origins of the universe, there is still no way to account for the missing dark matter that makes up for as much as a quarter of all matter in the universe. That's why a trio of researchers has proposed a new dark matter theory, which could explain how dark matter came about. We know dark matter exists because we can observe how its gravity interacts with visible matter and electromagnetic radiation. There is something there, although we can't yet see it, or put a finger on what it is. What is dark matter? In the new study, Evan McDonough and Stephen Alexander from Brown University, with David Spergel from Princeton University, suggest that a mechanism involving gravitational waves, basically, ripples in the fabric of space and time, first theorized by Einstein and confirmed to exist only in 2016, could explain how dark matter came to be. McDonough's team used a model of the primordial universe that assumed the presence of particles called dark matter quarks, which aren't the same as today's dark matter. These dark quarks could have a property called chirality, referring to the way the particles twist, similar to neutrinos. The chirality or handedness of these dark quarks could have then interacted with the chiral gravitational waves in the early universe, producing the kind of dark matter we have today. Lighter and wimpier, supposedly, as the universe settled into a cooler state, the interactions between chiral dark quarks and chiral gravitational waves resulted in a small excess of the former. These condensed into a quirky state of matter called a superfluid, which could still exist as a background field today. What we know to be dark matter are proposed as excitations of this background field, in the same way photons are excitations of an electromagnetic field. Interestingly, the dark matter particles resulting from such a model would be lighter than what's known as weakly interacting massive particles, WIMPs, which many researchers believe could make up dark matter. There hasn't been enough evidence to suggest, however, that this is the case. At any rate, being lighter than WIMPs would mean that dark matter wouldn't interact with normal matter. It's much wimpier than WIMPs, Spergel told New Scientist. As such, this dark matter theory could change how we should look for dark matter, as it wouldn't be possible to see such particles directly at all. Unlike WIMPs, these particles would also be distributed more evenly across the galaxy. At the same time, the ratio of dark matter and normal matter wouldn't necessarily be constant throughout the universe. Spergel explained, however, that this unique behavior could also provide us with a way to find dark matter. A more uniform, non-cluster distribution of dark matter could spill over into cosmic microwave background, the Big Bang's residual radiation, and produce a unique signature. It could even affect the formation of larger-scale structures, like galaxy clusters. It could also, perhaps, have an effect on gravitational waves. In any case, any new dark matter theory is certainly a welcome one, as experts continue exploring other possibilities to account for dark matter, or even dismiss it altogether. It's a cool idea, Stanford University's Michael Piskin, who wasn't part of the study, told New Scientist. Right now, dark matter is completely open. Anything you can do that brings in a new idea into this area, it opens a door. And then you have to walk down that corridor and see whether there are interesting things there that suggest new experiments. This opens another door.